Hey everybody, welcome to another stream. So let's continue with Nand2Tetris course. In this stream, we are going to build the last and final chip of project 3 section. So let's fire up the hardware simulator. Where's the file for program counter? It might be in A directory, I guess. Yeah, it is over here. pc.htl or like, let's open it up. pc.htl. Let's open up the slides as well. All right, so this is what we are going to build, a program counter chip, and this is the last chip of project 3 section. So program counter is basically something like this. Initially it will have a value of 0, and if reset is equal to reset is 1, then we set the program counter is equal to 0. So this will be the initial value anyway, and else if load is equal to load t is equal to 1, then we output the value which was inside input from the previous time unit. All right, so load basically gives out whatever was the value inside the in variable in the previous time unit, and if increment unit increment whatever, what is it called, a selector or something, increment selector is set to 1, then we increment the output by 1. Okay, and this program counter is of 16-bit, so we will have to use a 16-bit register to store the value of program counter. Let's try to create a diagram for the program counter in a paint program. Let's get a new canvas size of 1080 and 970 maybe. All right, so we know one thing, we need a 16-bit register to store the value of the program counter. So this is a register of 16-bit. So now this register will have its own set of inputs and outputs. Let's check the figure for register as well. So this is the figure for register. It will have a load operator, load input, sorry. It will have a load input and an input of size 16-bit. Also it will contain output of size 16-bit as well. So this is a 16-bit register, and it works like something like this. If the load bit is set as 1, then the input value, then we set the register according to the input value, or else the output remains the same, right? From the next icon onward, output emits the V. So don't store the input value until and unless the load bit is 1. And that's basically it for register. So to build a program counter now, initially it should contain 0. It will inevitably contain 0, so we don't have to set it. Now this, we need this load, which can be this one, I guess. This load for the program counter, can we directly apply this load to register? Also this incrementer will increase the value of the program counter by 1, so we also need an incrementer. I guess the incrementer was inside first chapter, I guess. We created the incrementer inside first chapter, maybe it was inside second. I guess it was inside second chapter. Incrementer 16, that's what we are going to use to implement the program counter as well. So incrementer 16 contains one input variable and one output variable. Whatever you pass it as input, it will increment it by 1 and provide it as the output. So suppose if I directly pass this output variable to our incrementer like this is our incrementer 16-bit, and we provide this output directly again to the input, then it will keep on incrementing the value. But we don't want to increment it by itself, we want some logic in between. So what logic? If incrementer bit is set to 1, then only we want to increment the value, or else it should remain as it is. This sequential logic seems a bit unintuitive because you have to think in terms of different time units, so it becomes challenging to implement sequential logic chips. Let's see, first the fetch instruction. It's the first instruction. This is equal to 0, this is 10 at. Okay, that we know. Go to this instruction. Alright, so we have this load bit for this kind of operation. Suppose if we don't only want to increment the value, but if we want to let's say right now the program counter contains value 16, but if we want to insert the value 20, then we can use this load variable, load input, set it to 1, provide 20 to this input, then it will set the program counter to 20. So that's what the load variable does. All right, so there's also this reset variable. So what reset does, it sets the output t plus 1 is equal to 0, this to 0. All right, but shouldn't we just say that the input t plus 1 is equal to, okay, the output should be 0. That means the value inside the program counter should be 0 as well. Let's try to load the simple register first of all to check how it works. This is the 16-bit register that we made. So now if I give 12 as value to the input and do tick and talk, nothing happens because we haven't set the load unit. If we set it as 1 and do tick talk, then after talk we have got 12 inside output as well. So now it will remain as it is. If I do 0, nothing will change. But now if I do 1 and change the value of input to say 1, let's say 3, and now if I do tick tock, then the output variable output will contain 3. So that's the basic functionality of a register. Now we have to use this register inside our program counter. So let's try to think in terms of time unit as well. When I say think in terms of time unit, I mean this kind of diagram. So wait, have they given this kind of diagram for program counter as well? This is for 1-bit register only. Guess they have not given. They might have given hints and at the end, I guess. They say that program counter can be built from a register. That much we know. An incrementer and some logic gates. Yeah, we know that. Now we have to implement some logic between them. So this logic gates are the main part, because there's nothing much to register and an incrementer. It just does what it does, but we have to apply some kind of logic. So let's pick just one functionality first. Let's pick load. Load is equal to this thing. What we want to do in case of load is the output should contain the input. The output should contain the input. So that's the basic functionality of a register anyway. So let's get the register first of all. Register. I will have to check how does a register look like. It's inside. Let's open up the HTML file of register for the reference. So register has an input, a load, and an output. So let's get the input variable. You can provide this input variable directly, and both are of 16-bit only, so that's not an issue over there. That's also a load variable. We can provide the load variable directly as well, and for the output variable in the same case. Okay, we have got register working. Let's open it up in the hardware simulator. To open the program counter. Okay, we have input, load, increment. So if I provide 16, 12, and if I do TikTok, nothing happens. But if I change the load bit to 1 and do TikTok, wait, if I provide 2 over here, if I do TikTok, nothing happens. But if I do this and TikTok, then the value gets loaded to the output. So we have implemented this functionality. Output variable the next output variable at the next time unit should contain the input variable from the previous time unit if load is set to 1. Now what we want to do, we want, if incrementer is set to 1, then the output should be the previous output plus 1. All right, So the output should be previous output plus 1. So for that we will have to use the incrementer. But there's one question in this case. If incrementer is set to 1, do we only have to provide the output variable as plus 1, or do we have to set the program counter value to plus 1 as well? Because I can do directly something like this. This incrementer, if I place a mux over here, and for the selector bit if I provide incrementer, this should be a mux or demux. Yeah, it should be mux. And if I pass this to second input and pass the output directly to the first input and provide the output like this, so now if the incrementer bit is set to 0, then nothing happens. We get the output as it is. But if it is set to 1, then we get this incremented output. So I can do something like this, but yeah, this seems legit. So let's try to use that kind of logic. We need an incrementer and so let's first get the incrementer. It is something like int 16, I guess. Let's check the incrementer as well. It should be inside the built-in chips. Built-in chips and incrementer 16. Yes, this is what we want. Okay, so it just has an input variable, and for the input variable we pass output. I'm sure this is going to give us errors. Then the output variable should go into output directly. And then let's use an intermediate variable over here. Let's call it v1, and let's pass this v1 over here. V1. Cool. So we have got the incrementer now. Now we want a mux. So mux 2a. A simple mux will suffice, I guess. Let's also check the HDL file of mux. Mux 16. Yeah, this is what we want. Mux 16. Wait, and it will, for the first input it will have v1, and for the second input, let's not directly pass it to the output variable. Let's keep it inside another input intermediate variable, which is v2. Now let's pass v2 as second input to the mux, and for the selector we are going to use the incrementer bit, and output should go directly into output. Let's try to run it. Let's reload it as well. Hopefully it is not giving us any errors. Let's try to check the TikTok functionality first of all. Okay, so nothing happens. Now if I pass incrementer 1 and do TikTok, for it just increments it by once only. So we don't want to increment it by once only. We want to increment it for all the clock cycles, or next clock cycle it should increment by 1 again and again. So that means don't only want this output variable here, but we also want to store this value as well. Does it mean that we have to set the load value as well? What if we set the load value and increment value both as 1? Then it only loads this value first. So what if we first set the increment value, it should increment the value. Why is it not incrementing the value? It was incrementing earlier, but now it isn't. It is saying that we have provided an illegal value. Why is it saying that? Why doesn't it increment? It was incrementing the value earlier, but now it is not incrementing. It's the issue. Okay, let's try to run it without setting the increment value. Now let's try to run it with the increment value set. Okay, nothing happens. We set the increment value initially. Now if we do, then nothing happens. But whenever I set increment value as 1, this button lights up, which is evolve, but it does nothing. So there is a flaw in our logic, I guess. So whenever we are setting the increment value, alright, maybe because of this register, we are setting the increment value as 1, and it should give us the v2 variable. But if v2 variable should contain whatever was inside v1 plus 1, and if whatever was inside was 0, and initially it should have 0. Wait, but initially Suppose if say I load 2 inside, then 2 has been loaded. Now if I do incremental and set the load bit as 0 as well. Now if I try to do tick tock, then it is incrementing, but it only increments it for 1 clock cycle. We want it to increment for all the clock cycles. Also, there's this thing that we have to first load the value to increment it. But if we place 0 initially, doesn't that mean that we are loading it? Suppose if I do something like this, let's first reset it. Now let's give load value 1. Now if I do tick tock, then technically it should load 0 inside the register. Now if I do 0 over here and 1 as the incremental bit, now it should increment the value, and it does increment it, but it won't for the next clock cycle. So I guess because we have to provide that output to input again, so we have whatever was output, we have to provide it again to the input for the incrementer to increment it. So the value is not persisting, so this implementation doesn't look right. We want something like this. This should go inside this directly. This is not the part we want. This should go, but take as per the implementation of the register, this output should be clocked to the input anyway. Maybe after each clock cycle we have to change the load bit. If we do something like this, after loading the value, now wait, suppose I keep load value as 1 as well. Now if I do tick tock, okay, nothing is going to happen anymore. If I set both value as 1 initially and do tick tock, nothing happens. But if I set increment as 1 only and load as 0, if I do tick tock, nothing happens. But if I set load as 1 first, increment as 0, and if I do tick tock, and now if I do increment 1, load 0, then wait, it is not giving us the output again. We have to reset it, I guess. Suppose if we reset it again, and now if we pass load bit 1 and do 1 clock cycle, and now if we pass increment bit 1, change this to 0 and do clock cycle, is there uncertainty in this case? Sometimes it works, sometimes it doesn't. This has something to do with the sequential logic. All right, how do we implement the program counter? I think I'm not able to implement the program counter because there's some fuzziness in my understanding of the register itself. I mean, I know how it works, but I think I don't know exactly how it works inside the simulator. So if I can just understand how it works, then maybe I will be able to implement the program counter as well. So this is the diagram of one 16-bit register. So it seems very simple that whenever the load bit is set to 1, we store the value. If I look at this diagram, whenever the load bit is set to 1, at the next time unit we will have whatever was inside the input value in the previous time unit. So for time is equal to t plus t2, we will have whatever was inside input variable t1 at t1 time whenever the load bit was set to 1. Now if we change the load bit to 0, it remains constant as long as we don't change the load variable. Now if we change the load variable and provide 0 as the input, then for the next time unit the value will turn out as 0 as well. So the value only changes on the next time unit. If the value changes on the next time unit, now we have to implement a logic on top of this 1-bit register, right? Not 1-bit register, 16-bit register, but we can imagine that there are 16 registers of this kind. Okay, so we have to implement something on top of 16-bit registers so that we get a functionality of a program counter. Let's try to think in terms of this code as well. So when I provide the input to this register and for the first clock cycle, after doing tick and tock, which is basically changing the clock cycle, so after doing tick tock it will be the second clock cycle, and on the second clock cycle I will have the whatever was its input variable if the load variable was set, right? Now if the load variable was not set, I won't have the value inside this variable, so I have to set the load variable to get the value in this v1 variable. So if I do tick tock, nothing happens. Even if I change this value to 12 and do tick tock, nothing happens. But when I change this value to 1, load value to 1, and do tick tock, we get, oh wait, we are also getting the incremented value inside v2. Why are we getting the incremented value even if this incrementer is not set to 1? Oh, okay, so we are anyway incrementing the value of v1 and store it inside v2. So now if I set this variable to 1, what is going to happen? Incrementer is set to 1. For the next clock cycle, what will happen? It will select V2, whatever was inside V2, and whatever was inside V2 will have changed, because I might have to check the implementation. We have implemented bed register. Let's check the implementation of RAM. Maybe that will give us some idea. This is the implementation of RAM. There's nothing much to it. It's just 8 registers stacked together. Let's try to work it through this diagram. So initially, let's walk through the one example. Suppose initially load bit is set to 0 and the increment bit is set to 0 as well. So now if we pass value to this input, we don't get it inside this output variable on the next clock cycles, because we are not setting this load variable. Now suppose if we set this load variable as 1, now we will get this input value inside output on the next clock cycle, and on that same clock cycle we will also get this incrementer value inside this v2 variable. But as the incrementer bit is not set to 1, we will only get this whatever was inside output inside this output and only. So basically it will retain the input. Now if we increment the clock cycle again, then what it does, the output variable remains the same, because the input variable was input variable remains same. Now if we change the input variable on the next clock cycle and do the clock cycle, then the output variables also change. So suppose if we want to increment this value, if we pass 1 to this incrementer, then we may get the incremented value for that clock cycle, but we also want that value to be stored inside this load variable. So whenever we do incrementer is equal to 1, we also have to set the load bit equal to 1 to store this value back to the register. Is that correct? It is complicated because of the combination of these 3 different inputs. We have to keep in mind the permutation, different combinations of load and increment and reset. To tackle that, let's try to draw the truth table. This truth table will be much more complicated because of the sequential logic. We have input, we have load, we have incrementer, we have reset, and we have the output. Now if we pass 12 to input, let's keep it as input. If the load bit is 0, incrementer bit is 0, and the set bit is 0, then whatever was output will remain as it is. Now if we change the load bit to 1, let's keep the load bit 0, incrementer bit 0 as well, and the reset bit to 1. Now we get now the output should be set to 0 when the reset bit is 1, and if incrementer 0, incrementer is set to 1, reset is 0, then when incrementer bit is set to 1, we want output as output. For the next clock cycle, right? For the next clock cycle, it should be output of this clock cycle plus 1. That's what this HDL file says anyway. Incrementer is set to 1. We want output is equal to output t plus 1. Cool. Output is equal to, so it should happen only after one clock cycle. And if incrementer input is input, load bit is 0, this is 1, this is 1 as well. Well, we can't have this kind of input, right? If incrementer is set to 1 and reset is set to 1 as well, a reset overrides all other inputs. So if reset is set to 1, then the output next output should be 0 anyway. Right, should be 0 regardless. So whenever the reset bit is set to 1, the output next output should be 0 regardless of these 2 bits. Okay, and if the load bit is set to 1, then regardless of the incrementer bit, we have to pass it to the output. But if both load and incrementer is set to 1, then we have to pass it incremented by 1. if we do something like this, whenever the incrementer bit is set to 1, we also change the load bit to 1, because we want to retain this incremented output as well. So we have to apply some kind of logic to these two bits, load and incrementer. Whenever the incrementer bit is 1, okay, we want something like this. Whenever the increment bit is 1, we want some intermediate variable n1 as the incrementer as 1. But when it is not set to 1, this incrementer bit, then we want L1 same as the load bit. So we can use a mux for this kind of functionality. Let's use a 1-bit mux. We don't want a 16-bit mux for this functionality. For A, we'll pass load, let's say, and for B we will pass true, and we will pass the selector bit as incrementer, and we'll get the output inside L1. Okay, we have this functionality now. Whenever the increment bit will be 0, then we will have the load inside L1, but whenever it will be 1, we will have true inside L1. Now we want to use this L1 over here, not the load but L1. Let's try to run it now. It is saying that true has no source pin. What do you mean true has no source pin? Wait, do I have to provide true like this? Lowercase true? Okay, so I have to provide lowercase true. Cool. Now it is loading. Now for all the clock cycle it doesn't do anything, but now if we provide load as 1 and input some value 8 and do clock cycle, it will have 8 inside the output. Now if I provide increment 1, load 0, then 1, 2, 3, 4, it only incremented it once. Because this value was not stored back into the input, and it was not stored back into the input because, well, the L1 was 1, right? Then it should have stored it. Let me walk through the diagram to figure out what it is doing. What if I try to load a test script? So when the incrementer bit is 1, the output should be, wait, the output does contain 1. Then why did it give us error? When incrementer bit was set to 1, we did get the output variable 1. So it was incremented. Maybe it was not incremented on the correct clock cycle. If I do 1 over here, 1, if I do tick and talk, tick and talk, tick and talk, yeah, nothing happens. The output doesn't change because, wait, the output doesn't change because the load variable is 1, and whenever the load variable is 1, this register retains the output v1 value, and which is 0. Great. So I guess this logic of ours doesn't really work. We can't provide L1 over here. We have to provide the load variable itself. Now if we provide load variable, if we provide the load variable, zero, 1th clock cycle, it should be 0, 1 plus 1. When we set the incrementer bit to 1, the next clock cycle it should increment the value. The next clock cycle it should again increment 2 plus, now at 3 and 3 plus it should increment. So as long as the incrementer beta is 1, we should keep on incrementing the output. But here the load variable is also set to 1. That means on the next clock cycle we will load this value to the output. Okay, so when the load bit is set, when the load bit is set, it overrides the incrementer. We don't increment it. But only when we set 0 incremental load to 0, then there is an effect of this incrementer bit. Great. And the reset bit overrides all these two variables. So on the 7 plus 1 clock cycle, if we pass reset bit as 1, and on the 8th clock cycle we will set this value as 0, and the 8 plus 1, if we pass 1 1, then for the 9th we will load the value. Let's walk through this thing again. Initially we have a register which passes output if the load bit is set to 1. Output to V1. It passes the output to V1. We also doing the incrementation V1 and V2, and we are providing it to mux and doing a selection. But this is not correct, because whenever the load bit is set to 1, you only want to load the output. This increment variable should not take effect, but in our case it will take effect. Because if the incremental bit is 1, we will be passing the incremented value to the output anyway. But you don't want to do this thing. So to this mux, we shouldn't directly pass the incrementer bit as the selector. We should pass an intermediate variable, and that intermediate variable should contain this kind of logic. It should contain, suppose the incrementer intermediate variable is called S1, then either it should contain a load and it should contain the incrementer. So if the load is set to 1, whatever the value of load is, it should be inside S1. Wait, I mean, if the load is set to 1, Okay, if the load is set to 1, we should pass the negation of load, or else if it is 0, then we should pass the incrementer bit directly. But if increment bit is 0 as well, then this S1 will contain, if load bit and incrementer bit both are 0, then we have to do this thing. Output should be output. Yes, this will work, I guess. So how do we get this variable S1? Should either contain the negation or the incrementer. So the truth table should look something like this. L, let's create a truth table for this variable. First bit, is load, second bit is incrementer, and we want the output S1. So 0 0 0 0 1 1 0 1 1. So when both are 0, S1 should contain 0. When both are 1, when it is 0 and 1, it should contain 1. And if it is 1 and 0, it should contain 0. And if both are 1, it should contain the load bit. Both are 1, it should contain 0. So only in case of load 0, only in this case the S1 should be 1 when the load and the incrementer is 0 and 1. So it should be something like this. Not of load and inc. And yeah, that's what we did over here. So if I do that, if we first of all we will have to get the not of load NL, let's call it NL. and here to get the end of A is equal to and L, B is equal to int, and the output should be S1. Cool. Now if we pass this S1 bit over here, then now let's see what happens. Let's also load the test script. Let it run now. Oops, it gives us error at this. Okay, it should contain 0, but our program contains 1 when the incrementer bit is set to 1. Now why is it incrementing? If incrementer bit is set to 1, because incrementer bit is set to 1 and load bit is set to 0, therefore we are incrementing it. So which is correct, isn't it? But we don't want the incremented value directly, we want it on the next clock cycle. Okay, let me stretch a little bit. We are getting the output directly in this clock cycle as per the results. So whenever the increment bit is set to 1, we directly get the output in that clock cycle only. But we have to let this clock cycle finish. So 1 plus and 2. At 2 we have to increment the output. So that means the outputs are not clocked. It must be because of this input variables. Also, how do we implement this reset bit? When the reset bit is set to 1, it overrides load and incrementer and sets the next output as 0. What if we use 3 different registers? Wait, to implement this reset bit, suppose if we use something like this, we don't directly pass this input variable to register, but if the reset bit is 0, if it is 1, then we place 1 inside, let's say one intermediate variable is v1, and if the reset bit is 1, we set it to 0 and pass it to this register. And in that case also we have to provide load bit as 1. See, this thing is common in all the cases, output t plus 1. So whatever the input, the outputs should change on the next clock cycle only. Whatever will be the input. If I keep this load bit as true and only change this the variable over here for all these cases, then it might work. So if I select v1 is over here, and if the reset bit is 1, then I change it to 0. If the load bit is 1, if the reset bit is not 1, then if I check the load bit, if load bit is 1, then I set this thing to whatever we get inside that input variable. And if this load bit is also not 1, then I check the incrementer bit, and then I pass the output +1. So how do I get output? Should be inside output. So in that case I pass output +1 to the input. Let's try to implement something like that. Let's connect this one as well as this one. I should use a mux, but we have to use a 3-way mux, I guess. Or we can use the 4-way mux. Let's check the 4-way mux. Mux 4-way 16. Yes, this is what we want. Let's use the 4-way mux over here. Mux 4-way 16. This mux, for the first value, it will have wait, but how will we use this selector bit? The selector bit is of 2 bytes, 2 bits, and this 2 bits will be something like this: 0001 101. And we have this kind of combination for reset, load, and inc. 0 0 0 0 1 1 1 1 0 0 0 1 0 1 1 0 0 0 1 1 0 and 1 1. So we have to map these things to this two selector bits, and then whenever the reset bit is selected for all of this, we don't care about load and increment. We want 0 0. But if selector bit is if reset bit is 0, then we care about load bit, and if load bit is 0 as well, then we care about the incrementer bit, and incrementer bit is 0, then this last case will happen. Marks 4v60. I'm trying to think of a way where we don't have to use a Mux 4v16 and still get this kind of functionality. Because when I think about implementing it this way using Mux 4v16, it gets much more complicated. We will have to make this kind of logic to map from this inputs to this inputs. Let's first of all check the implementation, not the implementation, the working of the inbuilt program counter. This is the inbuilt program counter, and if we check it, there's nothing happening. But if I change load bit to, wait, if I change the increment bit to 1 and do incrementation, then we can see the program counter is changing. With the output is changing on even on the half clock cycle, but this output doesn't change on the half clock cycle, it changes on the full clock cycle like this. And we also have inc, load and reset. All of these are clocked. વિડિયો ઉતારે છે. જાન Okay, these pins are clock. So do we have to declare these pins as clock inside our implementation as well? We didn't do something like that in RAM implementation. Yeah, we didn't declare them as clock, so we shouldn't do it inside program counter as well. Let's open up our implementation program counter. Okay, this is our implementation now. What do we do? It's been 1.5 hours and we are not anywhere close to implementing our program counter. It is saying a 16-bit counter with load and reset and control bits. Those are control bits. If reset bit is set to 1, output should be 0. Now, how do we influence the output? We can't directly set the output, but we can set the output using the load bit and this input bit. So I guess we might have to use mux 4OS16 implementation anyway. So we do have to map this inputs to where did the selector go? We have to map this include inputs to this inputs 0 0 0 1 1 0 and 1 1. Now this first bit should be 1 when either reset or load are 1, right? And this bit will be 1 when load is 1. Let's write the selector bits over here. Selector bit 0, selector bit 1. So now we want this bit 0. Selector bit will be 0 for, let's see, for this case, this case, this case as well, and this case. Whenever there is reset bit is 1, also over here as well, because here the load bit is also 1. Whenever the either of the load or reset bit is 1, we have to keep the selector bit 0 as 0, and it should be 1 on the remaining cases. In the remaining cases, I mean, and this selector bit 1 should be 0 and the selector bit 0 is 0. No, it should be 0 when in this case 0 0 0 0. Only when the reset bit is 1 and the selector bit 0 is 0, then we have to set the selector bit 1 to 0. It will also be 0 in this case. should be 0 in this case as well. And in either of this case, any or in the remaining cases, it should be 1. Now this selector bits, does it cover all the cases? Because you see it will be 0 0 for all of these cases, and it will be 0 1 for these cases, and it will be 1 0 for this case, and 1 1 for, yeah, it does take care of all the inputs. Great. Now we only have to map this thing to this. We have to find some kind of logic. Right, it won't be that much harder. Let's see, selector bit 0 should be 1 when not of res and not of load and not of ink, then only it will be 1. Or it will be 1 in case where not of res and not of load and ink. Cool. This is the equation for selection bit 0. Now for 1 is a bit more complicated because we have 3 of this. The first will be similar. Second will be this one for this inputs. So for those inputs, not of res and load and not of ink. Great. And it is almost similar. The last one is almost similar, only this will be ink. Now we have to reduce these equations. When both of these inputs reset and load are 0, then the selector bit will be 1 whenever this result and load bit are 0, regardless of the incrementer bit. So we can get rid of this. We can get rid of this thing. So now we only have to reduce this equation. Not of or of something is or 1 of or is equal to same. We can directly write it like this. We can get rid of this as well. So this will be the equation for selection bit 0. Now for 1, This one selected bit 1 is 1 wherever, let's see, first of all it is 1 where result S1 is 1 whenever this result bit is 0 and this 2 when load is 0 and increment is 1. When load is not 0 and increment is not 1. So we can write it like this: not res and not off, not load and inc. So this will be the equation for selector bit 1. We can reduce it further like this. If we apply not inside, not of this, and let's check the boolean identities, not of it gets converted to this form. So if we apply not inside, then it will look something like this: load or not in. Great. So this is the equation for selector bit 1. But in this case, this will give us 1 or 0. 1, yeah, it will give correct answer. In this case, it will give 1 or 1, 1 again. In this case, it will give 0 or 0. So it will give 0. Great. And in this case, 0 or 1. Great. So this equation works as well. So we have got the equation for selector bit 0 and 1. Let's try to implement it now. First of all, we have to get the negated portion of the input. So we have to use a not get. First, let's get not for the reset bit. Reset output, let's call it not res. Second will be for the load bit. This will be for the load bit, and third we also want a negation of incrementer. Let's call it not ink. Now we have to get equations for selector bit 0. So first, to get selector bit 0, we just have to end the negation of res and load. So let's get end, and first A will be not res, B will be not load, and output should go into cell 0. Correct. And for this part, first we have to get this OR, and then we have to end. So let's get the OR first. We have to OR the load with not ink. Let's pass it to an intermediate variable m1, and let an end variable. A will be not of res, B will be m1, and output should be selected bit 1. Right, we have got this selected bits now. Now all we have to do, right? So I was saying that we have got the selector bits. Now we have to pass it to the multiplexer. We got selector bit. Now we have to give A, B, and C, and D. So let's do that. For the A, we will have all zeros, so false. B will be B is wait, it is load. So load means we have to pass the input. And how do we pass the input? Like this. And C will be the incremented part. So we have to pass V2. Let's call it ink1. And this ink1 is over here. Let's take it over here. This should be input, and called ink1. Good. We have, wait, we have to increment the, wait, we are not yet to this incremental part. We first have to load it. So to get the loader, but we have already got the loader. So for incrementer, we will get the output and do the incrementer thing. So we can't provide it the input, we have to provide it the output. Let's see what happens if we provide the input. Cool, we have got the incrementer part as well. Now for the last part, it will just be output. For this one v1, for this register, here also we have to provide v1. Okay, we have got the functionality of multiplexer. We have to give the selector bits now. Selector bit 0 will be selector bit 0. Selector bit 1 will be selector bit 1. And then that's just output. R1. Let's call this output R1. Now we will pass R1 over here. Do we still need this mux? I think we don't need this mux. Let's get rid of it. But we do need this v1 variable inside the output. So we can use and like this, right? Input, we pass a as v1 and b is equal to true. And the output can go directly into the output. Let's try to load this program. The saying A1 and V1 have different bus widths on line number 30. Okay, yeah, all right. Because this is okay, we have to use a 16-bit AND. Is there something like a 16-bit AND? 35 true has no source pin. There's no 35. Okay, it should be lowercase. Great, now it is not giving us any errors. Now let's also load the test script and let it run. Okay, it passed this test, but it failed at this test. Let's check. It is not even loading the value inside the output. Do we at least have the incremented value? Well, let's see. Incremented, we have it inside incrementer 16, so we have it inside C, and it should go inside the R1. Why is it not inside R1 then? Selector bit is 0 is 1, and where's the selector bit 1? Okay, it is over here, 1 and 0. So 1 and 0 should select C, and if it should select C, R1 should contain the increment value, but it doesn't contain it. Why? Where's the bug? What is the value of R1 doesn't change? If I set the incrementer bit, then I should get this inside R1, but I'm not getting it. But am I getting it inside increment 1? Yeah, I'm getting 1 inside increment 1, and I'm passing this increment 1 to C. Now this C should be selected as per this variables. Is there a logical flaw in this thing? Because selected bit 0 is 1 and 1 in selected bit 1 is 0, so it is 1 0 1 0. If it is 1 0, it should select C, and C contains ink 1. Now this ink 1 should go inside R1, but that's not the case. Why? Okay, I get it. We have to change this load as well, right? This load should be true in all the cases. Now let's try to run it. It is still giving us the same error. If I check the output, why am I not getting the output inside R1? According to the mux logic, I should get the output. It is weird. Unless this R1 is getting changed by this thing. Alright, maybe that's the case. That can be possible. This V1 should change according to R1. Wait, have we used V1 twice? We have used V1 over here as well. What is V1 anyway? V1 is this output. Okay, I get it. Right, alright. V1 is this output. So what is happening is we are incrementing the V1, but V1 we are changing the value of V1 twice. No, we are not changing it over here. Let's see. At time is equal to t0, all of these inputs are 0, so an output is 0. Now when we set the incrementer by 1, what happens is over here, something happens over here. We select c is equal to inc1 and pass it to R1, but c is equal to inc1 comes from input 1 and v1 was 0. v1 was 0 if we increment it by 1. Okay, when I set the ink to 1 and to tick, then ink has been set to 1. Now if I do another step, because I guess man, this is hard. Mhm. Let's go back to the diagram. Suppose if we were to go with our initial solution and use one register and pass the input directly and keep this load bit the same as this load bit. Wait, of course we have to keep this load bit different because that load bit means that we have to save the previous output as input, but this load but we are also saving different outputs as well, so we have to keep this load bit separate from this load bit which we are given. Cool. So this load bit should be 0 or 1. When should it be 0? For all of these 4 cases, for all these 3 cases we are changing the state of the register, but for this 4th case we are not changing the state, we are getting whatever was in the previous output. So this load bit which is inside the register should be 0 for this last case and 1 for all of this case. Now when I keep this load bit as 1 for all these cases, I should provide the input. Now this input comes from, for first case, this input comes from the output directly. No, sorry, the input is 0 for the first case. For the second case, the input is whatever input we provide inside this variable. And for the third case, the input is whatever the output gives us plus 1, right? can still keep this logic, or I should say this logic, because it helps us select all of these four cases. But instead of passing this kind of inputs, well, I guess we can pass this kind of inputs. We pass, for first case we have to pass false, for second case we have to pass the input, for third case we have to pass the incrementation of input, and for fourth case we have to pass whatever was the output, and put it inside R1. Now this register, the load value of register should be 0 for this last case, and this last case is determined by 1 and 1, this port selector bit. So I have to use one NAND gate, and for the first input I provide selector bit 0, for second input I provide selector bit 1, and get output inside, let's say, n1 variable. Now this n1 variable will be 1 for only, will be 0 for this case. Yeah, I can directly pass this n1 variable inside this register. Now this register will be, load will be 0 for just this case, or else it will be 1. So now I can directly pass n1 variable over here. So we have provided the functionality where this load register will only load in these three cases, or else it will remain as 0. Now it should load from the R1, and R1 contains first is false, second is input, third is incrementer. Now this last two cases are somewhat problematic. Let's try to run it anyway. Great. Oh, not great. It isn't working in this case as well. Nothing really changed. So wait, so what did we do? We just changed the n1 variable over here. So now this load will be 0 for this final case. It will be 0 means inside b1 v1 will remain whatever it was, and what was it? It was this r1 still remains 0. It should be 1. It is not 1 because maybe because this r1 register, r1 variable gets clocked. So if I use say r11 over here, now if I pass r1 to r11, a is equal to r11, b is equal to true, and output equal to r. I do something like this, then let's see what happens. It's saying that a11 and have different width. We have to use n16. Right, but this r11 is not just a binary number. We can't directly pass it to r1. It also contains, well, yeah, it will work. Okay. And the r11 remains 0. So this didn't really change anything. Let's delete it. What's the issue? Maybe the issue lies in v1 variable. Because if we see, when initially everything is 0, means it's this case, when everything is 0. If I remove the intermediate variables, um, what if I remove this intermediate variable and directly pass, you know, output, and over here I pass output. I guess this is it for this stream. We will continue this implementing this chip in the next stream. I will see you guys in the next stream. So bye bye.